Welcome all to Newton's laws of motion class 10, in which we'll discuss about constraint motion. The meaning of word constraint is nothing but restricted. So if the motion of an object is restricted or decided by the motion of another one, then we call it as nothing but a constraint motion. As an example, suppose if you are considering a pulley system over here, assume that we are having a smooth pulley and a string is passing through the pulley, and one end of the string is connected to a block of mass m1 and the other end is passing through, other end is connected to a block of mass, let's say, that is equal to m2. The situation we already discussed in a two machine. So over here, if we are considering that this string is inextensible, if this mass m2 is moving in downward direction with an acceleration a, definitely this m1 should move in upward direction with an acceleration a. So we can say that the acceleration of m1 is constrained by the acceleration of m2. So if while exerting some force on m2, suppose if we are making the acceleration of 2 as 10 meter per second in downward direction, definitely m1 is constrained to move with the same acceleration. So these type of motion, where the motion of one object is constrained by the motion of another object, is known as nothing but a constraint motion, and we'll discuss about some different constraint relations that we are using in Newton's laws of motion. So first part, we'll discuss about the constraint relation for a rigid rod. Over here we are just considering a rigid rod of length L, which is kept in contact with the smooth vertical and horizontal surface, and let's say at this instant it's making an angle theta with respect to the horizontal. Now assume that this end over here, let's say end A, is at a distance y from the origin, and this end B over here is at a distance x from the origin. Now if you are left it to move, so due to the force exerted by gravity, and we consider that it's a frictionless surface, the object may move something like this. So the object may move something like this, so that the y component is keep on decreasing and the x component is keep on increasing. So at an instant, assume that this point A is moving downward with a velocity, take it as VA, and this point B is moving towards right with a velocity, take it as VB. And we are going to find out what about the relation between velocity of point A and velocity of point B. Now if you are just considering that length of this string is nothing but L, now from this right angle triangle we can write the relation between x, y and L, that is x square plus y square is equal to nothing but L square. Now if you are differentiating this equation with respect to time, we'll get the answer as something but 2 into differentiation of x square, we can take as 2x into dx divided by dt, plus differentiation of y square, we can take it as 2y into dy divided by dt is equal to differentiation of L square, we can take it as something but 2L into dl divided by dt. Now this can be written as 2 into x into dx by dt is representing the value of velocity of point B, because it is a velocity at the rate at which the value of distance x is varying. So this we can take it as something but velocity of point B, plus 2 into y into this dy by dt is representing the rate of change of y, which is nothing but the velocity of point A. So we can write this is equal to nothing but VA. And here you can observe an important thing is that with respect to time the value of y is decreasing, so dy is a negative value. So we can put a negative value over here as the value of y is decreasing, is equal to nothing but 2 into L into dl by dt, as the length of rod is a constant, it is not going to change, the value of dl by dt is 0, or you can write this as equal to 0 over here. So you can write 2x into velocity of point B is equal to 2y into velocity of A. We can cancel this 2 and you can write the velocity of B is equal to nothing but y divided by x into velocity of A. Or you can write velocity of B is equal to, now from this triangle we can observe that over here this is taken as nothing but x, this is taken as y, and this is taken as theta. So we can write from this right angle triangle we can write tan theta is y by x, so instead of this y by x we can write it as tan theta into velocity of point A. So this is a constraint relation between velocity of A and velocity of B. So if you know the value of velocity of A, we can find out the value of B, or if you know the value of B, we can find out the value of A by using this constraint relation. Now we'll discuss another technique to find out this constraint relation for any type of rigid body. So if you are just considering any type of rigid body over here, it may be moving with some different type of velocities in different directions. So over here, if I'm just considering a particle over here, take it as particle A, and another particle over here, I'm just considering that particle B over here. Okay, and we are just drawing a dotted line which is connecting this particle A and particle B. Now, if it is a rigid body, it can move in different directions with different velocities, but at any situation, the distance between point A and B will not change. It will be a constant always. So if at an instant, let's say this point A is moving along this direction with a velocity, take it as VA, and at the same instant, just assume that this particle B is moving along this direction, let's say with the velocity VB, and with respect to the line joining particle A and B, let's say this VA is making an angle theta 1, and this is making an angle, take it as theta 2. So we can just find out what about the component of velocities along the line joining point A and B. So component of VA along this direction, we can take it as something but VA cos theta 1, and component of B along this direction, we can take it as nothing but VB cos theta 2. So over here, the component of velocity along the line joining them should be same, because the distance between point A and B will be a constant. So over here, as the distance between point A and point B will not change, so the component of velocity along this direction, VA cos theta 1, should be equal to component of velocity along this direction, which is VB cos theta 2. If VA cos theta 1 is greater than VB cos theta 2, then the distance between A and B is going to decrease. If VB cos theta is greater than that of VA cos theta 1, then distance between them is going to increase. For a rigid body, distance between any two particles will not change. So we can say that the value of VA cos theta 1 should be equal to nothing but VB cos theta 2. We can use this constraint relation also to find out the relation between velocities of different particles in a rigid body. So just now we discussed the constraint relation for a rigid rod. We can find out the same thing by using this method also. Let's say this point A is moving downward direction with the velocity VA, and the point in contact with the ground is moving towards right with the velocity, take it as VB, and this angle we took it as nothing but theta. Now we can just find out what about the component of velocities along the line joining this point A and point B. So we are going to find out the component of this velocities along the line joining point A and B. So as this angle is equal to theta, we can write component of VB along this direction, that is equal to nothing but VB cos theta. Same as like that, if this angle is equal to theta and this angle is 90, so this angle is going to be nothing but 90 minus theta. So we can write this component is VA cos 90 minus theta, or we can write that is equal to VA sin theta. Now according to the concept of rigid body, the component of velocities along the line joining any two particles should be same. That means we can write the value of VA sin theta should be equal to VB cos theta, or you can write as VA sin theta by cos theta. We can write as tan theta should be equal to nothing but VB. So by using this method also, we can find out the constraint relation between velocity of point A and velocity of point B. Remember that for 2 points on rigid body, the component of velocity along the line joining these points always remains equal. Now we'll discuss about block string constraint relation. So over here, if you are just considering that there is a block A which is moving in downward direction with an instantaneous velocity, let's say that is equal to VA, and block over here, take it as block B, which is kept on a smooth horizontal surface, which is moving towards left with an acceleration or with an instantaneous velocity, take it as that is equal to VB. And our aim is to find out what about the relation between, or constraint relation between, velocity of block A and velocity of block B. Now assume that at this instant this string is making an angle theta with respect to velocity of a. Now if this block is moving in downward direction with the velocity va, so we can say that the string should also move in downward direction with the velocity va. The string over here is moving downward direction with the velocity va, then this string over here should move in upward direction with the velocity va. So we can say that this string should move along this direction with the velocity that is equal to nothing but va. Now over here at this stage students may get confused, that some students will write this va cos theta is equal to nothing but vb, and some students will write it as vb cos theta is equal to nothing but va. So over here just remember that this relation is wrong, and the correct relation is vb cos theta is equal to va. Now let's see why this constraint relation is correct. Because we cannot resolve the component further into different components. We can resolve only the actual component of velocity or actual velocity into its components. Means this block B, when this block A is moving in downward direction, this block B is not going to move in this direction. Got it? That means if you are just considering this block over here, when this block B is moving, it is going to move through a path something like this. So Vb is the actual component of velocity, in which direction actually the particle is moving. The block B is not going to move along this direction. So Va is the component and Vb is the actual velocity. So we need to write it like this: the component of actual velocity, that is Vb cos theta, should be equal to nothing but Va. So that is a constraint relation between them. So over here, no need to get confused. You can just consider always in this form. The velocity of block, just resolve the velocity of block along the direction of string. Don't resolve the velocity of string along the direction of block. Now we'll discuss about block pulley constraint relation. So over here we are having two situations. One is the constraint relation for a fixed pulley and the constraint relation for a movable pulley. Over here the pulley is smooth and it is fixed over here. So you can just say the direction of motion of these particles. Let's say this block A is moving downward direction with an instantaneous velocity Va, and this block B is moving in upward direction with an instantaneous velocity, take it as Vb. So as we know that if this string is inextensible, so velocity of A in downward direction should be equal to velocity of B in downward direction. So over here about the magnitude of velocity, we can say that the value of Va is equal to Vb for a fixed pulley. Now we'll discuss about the constraint relation for a movable pulley. If you are considering that string on the right side is displaced in downward direction by a distance x, and the string in left side is displaced by a distance, let's say, that is equal to y. So over here we can observe that the total length of the string which is getting free is nothing but x plus y due to displacement of string on the left side and right side. So we can find out what about the displacement which is happening to the pulley over here. So if the string is getting displaced by a distance that is equal to x plus y with respect to its initial position, so you can write the total length of this portion, means length of this part plus length of this part, should be equal to the length of pulley which is getting released, and that is equal to nothing but x plus y. So half of this portion is on left side and half of this portion on right side. So the displacement of pulley is going to be x plus y divided by 2. So over here you can say that this pulley is going to displace in downward direction by a distance, and that distance will be equal to nothing but x plus y divided by 2. So that is a constraint relation for a movable pulley. As an example, just consider that this string is getting released, and let's say string on the right side is getting released by a distance that is equal to, take it as 5 meter, and the string on the left side is getting displaced by a distance, let's say, that is equal to 50 meter. So here you can observe that the total length of the string which is getting free is nothing but 15 plus 5, that is equal to 20. So overall this distance means this distance plus this distance is going to be nothing but 15 plus 5, which is equal to 20. So out of 20, we can say that 10 is on the left side and 10 is on the right side. So this pulley is going to displaced by a distance that is equal to 10 meter. So for any string pulley system, we can use this constraint relation over here. So in general, we'll represent this constraint relation something like this. If we are representing the acceleration of pulley represented by A, and acceleration of string on right side is represented by X, and acceleration of string on left side is represented by Y. So we'll write the constraint relation between them is A is equal to X plus Y divided by 2. Now we can use the same equation for displacement, velocity as well as for acceleration. We'll take some few examples to understand this. Now just consider a situation that string on the left side of this pulley is moving upward with an acceleration of 10, and on the other side it is moving downward with an acceleration of 5. So over here this pulley will move in upward direction with an acceleration, let's say A. So you can write acceleration this pulley is equal to, over here you can take one particular direction as positive and other direction as negative. If I am taking upward direction as positive and downward direction as negative, so you can write our normal equation is X plus Y divided by 2. So over here it becomes A is equal to X, we can take it as something but plus 10, and Y we can take it as minus 5 as it is in downward direction divided by 2. So we'll get the answer as something but 5 divided by 2 or 2.5 meter per second. So this pulley is going to move in upward direction with an acceleration of 2.5 meter per second square. Now just consider another example. In this, let's say this block A is moving downward direction with a velocity, instantaneous velocity, take it as VA. So if the block is moving downward direction, this string will move in downward direction. So the string will move in upward direction. So this pulley will move in upward direction. And that pulley is connected with this block B. So this block B is going to move in upward direction with the velocity, take it as VB. And our aim is to find out what about the velocity or the relation between these velocities or constraint relation between these two velocities. So for the calculation, we'll write it something like this. If this block is moving downward direction with the velocity VA, this string is going to move downward with the velocity VA. So this string is going to move upward direction with the velocity VA. And you can observe that this string over here is attached with a rigid support, so it will not move. So velocity this will be equal to 0. So we can identify what about the constraint relation for this pulley. So if you are considering the constraint relation for this pulley, here you can observe that pulley on the right side is at rest and the string on the right side is at rest, which is having 0 velocity. And if you are considering the string on the left side, it is moving upward direction with the velocity VA, and this pulley is moving upward direction with the velocity, take it as VB. So by using our constraint relation, we can write velocity of this pulley is equal to velocity of A plus 0 divided by 2. So we'll get the constraint relation between them. Velocity of B will be equal to velocity of A divided by 2. So in the next part, we'll discuss about wedge constraint relation, in which over here we are considering a wedge which is having some angle alpha with respect to its horizontal. And if this wedge is moving towards right with the velocity, let's say that is equal to V1, then the block or the rod over here, we can observe that this will move in downward direction with some velocity. Let's say that velocity is represented by V2. And our aim is to find out what about the relation between this velocities V1 and V2. So over here you can observe the situation something like this. When this wedge is moving towards right with some particular velocity, then this block will move in downward direction. You can observe it something like this. Got it? So this will be the relation between velocity of V1 and V2. So the motion, you can once again observe that how it is moving. So as the block is moving towards right, so this rod is constrained to move only in vertically downward direction, so it will move something like this. And we are going to find out the constraint relation between them. So we can just consider that it's displaced this much when the rod hit the ground, something like this. If you are considering the situation with respect to its initial position, so the situation was something like this. So this is representing the displacement or velocity of rod, that is V2, and this is representing the velocity of wedge, that is, we can take it as nothing but V1. And this angle is equal to alpha. So from this right angle triangle, we can write the value of tan alpha is equal to opposite side, which is V2, divided by adjacent side V1. So we can write the constraint relation between them, that is V2 is equal to nothing but V1 tan alpha. Hope so that you understood what were the things we discussed in this class. If you are having any doubt, please contact. Thank you.